Taking our next example, the continuous assignment statement is assign E equals A multiplied by B. So this time, instead of the addition, we have the multiplication operator. As before, we'll use the same values for A and B. We start with our expression tree, which looks like this. We then identify the sizes for all quantities. So we've got A is 5, B is 5, and that comes from the declaration. We have a 5-bit vector, and E is a 7-bit vector of type wire. So E looks like this. Representing 7 wires. All of the arithmetic operators are context determined, which means for our example that we find the largest of the 3 values for the sizes. So 5, 5, and 7. And the largest value there is 7, thereby telling us that we do a 7-bit multiplication. And because it's a 7-bit multiplication, we now have to extend our 5-bit operand to 7 bits. And we do that by doing an unsigned extension. And the reason it's unsigned is that our multiplication is an unsigned multiplication. So unsigned indicates then that we have an unsigned extension. So we go from 5 to 7 bits. And in a similar manner, the second operand is extended from 5 to 7 bits, and it's also an unsigned extension. And our multiplication will yield a 7-bit result. We know that multiplying a 5-bit value by another 5-bit value yields a 10-bit result. But in our case here, we just have 7 bits. This is what Verilog will do for this particular example. And the reason we've 7 bits here is that we've determined the operation to be a 7-bit multiplication. We'll see on the next slide how to address this problem. So let's continue with this example. Our first operand has the value 11101, second operand 00010. When we perform an unsigned extension from 5 to 7 bits, we take our 5-bit value and insert zeros into the most significant bit positions into these 2 positions. That brings us from 5 to 7 bits, and the same for the second operand. We insert 2 zeros because of our unsigned extension. We now multiply these 2 values, and when we multiply these 2 values, the resulting value is given here. So the output of the multiplication is 0, 1, 1, 1, 0, 1, 0. Let's see if this makes sense. Well, we're multiplying A by B. A is the value 29 decimal. B is the value 2. So in decimal, we're multiplying 29 by 2, and that gives us the decimal value 58. And you can check to see that 58 is represented by this binary value. If you're ever unsure about these values, you can always use the calculator to check the correct result. So our base is decimal. So we've got 29 multiplied by 2. So the result is 58, and that's equivalent to the binary value 00111010, which is what we have. Our last step is to perform the assignment. We've no problem here because the output of the multiply is a 7-bit value, and we're assigning that to a 7-bit wire. So let's do that then. This is the LSB, least significant bit. If we assign this bit as our LSB, we have the following values: 0, 1, 0, 1, 1, 1, 0. And for our last example, let's take the assignment assign f equals a multiplied by b. These are the values we have for a and b. Each is a 5-bit value. And this time f is a 10-bit wire. So f looks like this, referring to the 10 wires. Our expression tree is as shown. Remember the steps. First of all, identify the sizes. So you've got 5, 5, and 10. 10 is the size for f. And from those three, we identify the largest value, which is 10. So that tells us that our multiplication is a 10-bit multiplication, thereby indicating the output is a 10-bit value. This 10-bit output is desirable because we have a 5-bit by a 5-bit value, and in order to guarantee the correct answer, we need to ensure that we have a 10-bit result. Our next step then is to extend our operands, performing an unsigned extension on each from 5 to 10 bits. And if we take our values for a and b, the 5-bit values are extended to these two 10-bit values, and performing that 10-bit multiplication yields this 10-bit value. I've accidentally deleted my 10 wires for f, so let's put them back in. So this is our 10-bit output, and that 10-bit value is then assigned to f. Again, no problems. We have a 10-bit value assigned to a 10-bit value. So the output of the multiply is 0, 0, 0, 1, 1, 1, 0, 1, 0. Again, noting the LSB and taking this wire as the LSB, the values on the 10 wires are as follows. And a nice feature of this example is no matter what 5-bit values we use for A and B, we can always represent our answer without error because we use a 10-bit result.